Hi guys, my name is Kennedy and I'm going to be going over autoencoders and their uses. So what is an autoencoder? An autoencoder is an unsupervised neural network that's used for dimensionality reduction. Dimensionality reduction means that we want to represent our data with a minimal number of features. You can think about this as a book. For example, every time we want to explain what happens in a book, we wouldn't want to have to read the entire book. Instead, we could extract the most important information out of this book and write a summary. This way, we have a shortened amount of data that we need in order to understand the main concepts and ideas inside of this book. Generally, autoencoders are made up of an encoder part and a decoder part. The encoder consists of an input layer of features, and then some number of hidden layers. And then in the middle, they will have their vector of latent variables here. Then they will have another layer of hidden layers, which would be the opposite of these layers. For example, if our hidden layers in the encoder was one layer of 3 and then one layer of 2, our decoder would have one layer of 2 nodes and then another layer of 3 nodes. Then lastly, our decoder will output the reconstruction of our input. The purpose of our autoencoder is to reconstruct the input that we give it. In order to train our autoencoder on how to do this, we penalize it with something called the reconstruction loss. The reconstruction loss is just a measure of how different the reconstructed input is from the given input. Our job is to make this difference very small so that our input and our reconstructed input is very similar. A basic autoencoder would be a vanilla autoencoder. This autoencoder has only one hidden layer, which is the layer of latent variables. The latent variables are the most important features we've extracted from the input layer. If we want to add more complexity to our autoencoder, we can introduce more hidden layers. In our multi-layer autoencoder, we would have hidden layers in between the input and latent variables, and then again, hidden layers in between the latent variables and the output. Depending on how complex you want your model to be, you may have many hidden layers in the encoder and in the decoder. Our first use case is feature extraction, which is similar to the first example I talked about when I talked about extracting a summary from a book. In this example, I'll use an audio file. Say you have a music file and you want to extract some important features in your music. You could input the music file as your input layer and then pipe it through the hidden layers. And then out would come as your latent variables the most prominent features in your music. These features could be things like the beat, any sounds that are repeated, if the artist is repetitively singing a high note. These features might be expected to show up. Finally, after going through the hidden layers in the decoder, your autoencoder will output the reconstructed music, which should be very similar to the music that was inputted in the beginning. Now you can input just the raw audio data, but in audio processing, it's common for the user to input either the FFT or the MFCC, which is the Mel frequency substral coefficients. They do this because these features are often difficult for the autoencoder to learn on their own, so we just give these features to it and use that as our input. Our data learns to reconstruct the music file by something called the reconstruction loss. The reconstruction loss, as I said earlier, is just a measurement of how well our autoencoder is at reconstructing its input. The reconstruction loss can be calculated many different ways, but we're going to use just a simple approach called the mean squared error. The mean squared error is just the input variable, which is the music file, minus the reconstructed music file, and then squared, and then you divide it by n, which is the total number of samples you have, which would just be taking an average, hence the name mean squared error. Our goal is to minimize this construction loss so that our input data is very similar to the reconstructed input that we have. The next use case I'll be talking about is denoising. In denoising, we'll have a data set of noise-free data. In this example, we'll be talking about hand-drawn digits. As a pre-processing step, we'll artificially add noise to these images so that they become these noisy hand-drawn digit images here. We want to reconstruct the original images using these noisy images. So after piping these images through our encoder layer, we would expect the latent variables to represent the features of the image without any noise. Then we'll use these latent variables to reconstruct the image, and hopefully our output will look something like the original image. Next, we'll talk about compression. When we think of data compression in autoencoders, we split up the encoder and the decoder into two parts. The encoder is used for the data compression, and the decoder is used for the data decompression. You can see here that in the compression step, we'll have our input data that will get piped through our hidden layer, and then out will come the extracted important features, which we call our latent variables. Then these same latent variables are used as input in the decoder part. If you have your compressed latent variables, you could share this information with a friend, and then he might use it on his machine in the decoder, which would decompress your compressed file and reconstruct it into its original format. The advantages of using autoencoders for data compression is that they can learn complex features about the data and create better compressions of the data. However, a disadvantage is that autoencoders are very specific to the data they were trained on. So if we trained our autoencoder to compress images of cats, it would be really bad at compressing images of dogs or anything else other than cats. Therefore, they're not generalizable and are not currently used in industry. Next, we'll be talking about a variational autoencoder. A variational autoencoder is similar to a regular autoencoder in structure in that it has an encoder part, a decoder part, and an input and a reconstructed input. It also has a set of hidden layers in the encoder and a set of hidden layers in the decoder. However, the latent variable space is different. Rather than outputting just the latent variables that we calculated, we output a mean and a standard deviation that describe a distribution of values these latent variables could take on. If you remember from a statistics class you took a long time ago, you might remember that a normal distribution looks something like this, with the mean down the center and a standard deviation describing the width. Variational autoencoders can be used for a task like data generation. In our example, we'll say that we're generating new pictures of human faces using images of human faces we already have. We would have our human faces as input, and our latent variables would be the mean and standard deviations we've calculated for characteristics that we found in these faces. For example, we might find that eye color, hair color, and skin tone are very important features in our image. Then our mean and standard deviation would describe how these variables are distributed. After this, we would output a reconstructed face, which might look very similar to our input, but may not. What do I mean when I say a distribution of latent variables? Well, if we had this picture of a man, we might calculate the latent variables to be smile, skin tone, gender, maybe a beard, glasses, and hair color. Then the distribution of latent variables would describe how each of these variables varies. If we were calculating just the regular latent variables for this picture, we would get only one value for skin tone. In this example, it's 0, but it may be over here closer to 1, or it may be over here closer to -1. The point is, we would only get one value. However, in a variational autoencoder, we would calculate a mean and a standard deviation. These would be used to describe a distribution that skin tone could take on. This distribution describes the values of skin tone for this specific image. It does not describe the values of all of the images in our data set, just the ones this image could take on. For the reconstruction phase, instead of using just one value for skin tone, we would take a sample from our distribution, say maybe here. Then whatever value the sample has, maybe it has a skin tone value of 0.5, we would use to reconstruct our input image. If we only used the one latent variable value 0 every time, we would always get the same reconstruction. However, because we're sampling from this distribution here, we will get a slightly different reconstruction for every sample we take along this distribution. Therefore, we'll generate new data given this man's face. Our data may look like the input data, but it also may vary. Given our distribution of latent vectors, if we were to plot them on a graph, they would look something like this. They would have this dark circle as a mean, and this wide cloudy area as a standard deviation, which means that this latent variable can take on any values within this cloudy region. Our latent variables would be clustered into regions where the data is similar. We can sample from any space within the distribution of these latent variables. However, what happens when we take a sample from somewhere in this blank area outside of our distributions? Our model hasn't been trained on any data in this blank space, so our model won't know what to do. Instead, it will output garbage. The solution is to train our data with something called KL divergence. KL divergence measures how well one distribution is at describing another distribution. We want our latent variables to be normally distributed so that there's no gaps in between the clusters. To do this, we'll train our latent variables to be distributed as a normal distribution. Because the KL divergence describes how well one distribution fits another, we can calculate the KL divergence between our latent variable distribution and our normal distribution, and then minimize this value so that the difference is minimal. This will cause our latent variables to be forced to a normal distribution. So using this new KL divergence function, we need to change our original loss function. Originally in our autoencoder, we just had the mean squared error as our reconstruction loss. Now, we'll also add the KL divergence to this so that we can minimize both of these at the same time. You can see here that if we use only the reconstruction loss, as in a regular autoencoder, we will have clusters of data, but there will be these big gaps between them, which is spaces that we can't take samples from. If we use only the KL divergence, we'll have our data normally distributed. However, there will be no clusters, so we won't know how to reconstruct our data. Using a combination of both of these, we'll have both clusters and a normal distribution so that we're able to both reconstruct our data from the important latent variables and sample from all points within the distribution. If we had a picture of a man without glasses as our input, and we sampled from our distribution with a glasses variable at a very high probability, we could expect our new image to be reconstructed with glasses, hence generating new facial data using our autoencoder. As a review, we went over feature extraction, which was just a regular autoencoder using mean squared error as our reconstruction loss. Then we went over denoising, which uses feature extraction to find the latent variables that describe our original data so that we can reconstruct it without the noise in it. Then we went over data compression, which we found was useful with autoencoders, however has some drawbacks because of their non-generalizability. And finally, we went over data generation, which uses a variational autoencoder, which is a little bit more complex than a regular autoencoder. Thanks for watching, and I hope this helped you on your journey through autoencoders.